Welcome to our review on superconductors. So if we think about our metals then, if we look at their structure, very high magnification, then what we find is that they have a structure that contains crystals, as you can see in the picture in the middle there. Now the reason that we get a crystal structure is because when we look at the particles in our metals, they're very closely packed together in that regular arrangement. So whenever we have that kind of structure, we'll generate crystals as a result. If you think back to when we looked at the structure of our metal, we know that metal crystals contain these delocalized electrons. And those electrons are actually free to move through the structure, and that means that the electricity is being conducted through the metal. Now, what we actually find is this isn't a nice smooth process. What we'll find is that there will be things like other electrons or the positive metal ions that get in the way of those moving electrons. Anytime we have something that blocks the passage of our electrons' motion, then we get electrical resistance. When we have electrical resistance, then we generate heat and we will waste energy. If we think about a superconductor then, this is quite simply a material with very little or even no resistance to the flow of electricity. So what we actually find then is that the resistance of all metals is going to decrease as we decrease the temperature. So the superconductors actually work by, at the moment, being very cold. So we actually have to use liquid nitrogen to cool them down. But when we've done that, we end up with something that has almost no resistance to the flow of electricity whatsoever. And if we've got no resistance, we won't be generating any heat, and therefore we won't be wasting any of our energy. One of the places that we're using these superconductors then is to make very powerful electromagnets in those MRI scanners that people use to view the insides of bodies in medicine. Now, in the future, we may also be able to use these superconductors for a couple of other things. First one being that we may be able to make very fast electronic circuits. So what we find in our current circuits is because we've got that electrical resistance, it slows down obviously the transmission of the electricity. If we had no resistance, it would be even faster than it is now, which means more powerful computers. Second one that we may be able to use superconductors for in the future is to replace all those metal cables that we have for power transmission. So if you think about the national grid and the fact we've got those big pylons with the cables trailing all the way across our country, if we were to replace those current metal wires with a superconductor, then what we'd find is we would lose very little energy through that power transmission. Because at the moment, as the electricity flows through those wires, we've got that electrical resistance there, which means we generate heat and therefore we lose some of the electricity between the power station and our homes. If we used a superconductor, we wouldn't have that resistance, we wouldn't generate the heat, and therefore we wouldn't lose that electricity between the power station and the homes, thereby making it a far more efficient process. There is one significant drawback we need to remember though. As I said at the beginning, at the moment when we look at our superconductors, they work in liquid nitrogen temperatures, very low temperatures. So we don't have one that can work at room temperature at the moment. They'll only work if they are very cold. So because of that, it obviously limits the number of uses that we have for them at the moment. If, however, we can come up with a superconductor that does work at room temperature, then that has such huge potential that we may see massive changes in terms of electrical circuitry and power transmission. But at the moment, because they need those very low temperatures to work, then we're rather limited in what we can use them for.